A raindrop strikes the surface of the ocean. For a fraction of a second, it exists as a small, perfect disturbance, a ring spreading outward, a dimple pressed into the surface by its own weight and speed. Then it crosses the boundary. It passes from air into water, and in the instant of that crossing, everything about how its energy moves through the world changes completely. The air it fell through carried it slowly. Sound in air moves at roughly 1,000 feet per second, fast enough by the measure of ordinary things, but modest by the standards of what waits below. The moment that same acoustic energy enters seawater, it accelerates. It travels at nearly a mile per second. It covers the length of a football field in the time it takes to blink. The ocean does not merely transmit sound. It seizes it, carries it, holds it close in a way that air, with its low density and its easy compressibility, cannot begin to approach. This is not a small difference. It is a transformation of kind. The raindrop's energy, crossing that surface boundary, has entered a medium so different from the one above that the two might as well be separate worlds. And in the deep water below, cold, dark, still, under pressures the body cannot feel and the mind can only reach for obliquely, that energy will travel in ways that take a long time to fully understand. Sound needs two things from any medium it moves through. It needs mass, because mass is what carries the pressure wave forward, and it needs stiffness, the tendency of a compressed material to spring back, because stiffness is what determines how fast the disturbance propagates from one region to the next. Air has neither in great abundance. Seawater has both. It is dense, carrying more than 800 times the mass per unit volume that air does, and it is stiff, far stiffer than air, resistant to compression in a way that forces any pressure wave to move through it with great speed. The technical name for this stiffness is the bulk modulus, and in seawater it is high enough to push the speed of sound well above 1,500 meters per second across most of the ocean. 1,500 meters per second across most of the ocean. 1,500 meters per second. In the open water, a sound made at one point reaches a spot a mile away in roughly 1 second. It covers the distance between two ships on the horizon in less time than it takes to draw a breath. The surface of the ocean seen from below is not what the surface looks like from above. From a boat, the ocean looks open, permeable, a skin between two worlds that anything might cross. From beneath, it is a ceiling, not a soft or ambiguous ceiling, but one that, from the perspective of sound, behaves almost like a mirror. The acoustic impedance of seawater, a measure of how much resistance the medium offers to the passage of a pressure wave, is more than 3,000 times higher than the acoustic impedance of air. When a sound wave moving through the water reaches that boundary and tries to cross into the air above, the mismatch is so extreme that nearly all of the energy reflects back downward. Almost none of it escapes. The surface acts as a seal, and the sound that strikes it from below is returned to the water almost intact, as though the sky above were simply not there. This is why the ocean is not merely a place where sound travels. It is a place where sound is kept. The water holds its sounds in a way that air cannot. A signal generated within the ocean tends to stay within the ocean, bouncing back from above, moving outward and downward and around, losing energy only slowly to the medium itself, and even more slowly to the boundaries on either side. For the right frequencies, for sounds whose wavelengths are long enough, whose energy is low enough in pitch, the ocean offers something close to acoustic permanence. The energy a sound loses to the medium itself as it travels is called absorption. In air, Absorption is significant even over modest distances. A shout fades within a few hundred feet, not only because it spreads outward in all directions, thinning as it goes, but because the air itself extracts energy from it through the motion of molecules, through heat, through the countless small inefficiencies of a gas. In seawater, at the lowest frequencies, absorption is almost negligible. At 20 cycles per second, 20 hertz, the absorption of sound in seawater is so small that a signal traveling 1,000 kilometers loses only 1/10 of a decibel to the water itself, 1/10, a barely measurable fraction of its original strength, surrendered across a distance greater than the width of Texas. 1/10 of a decibel per 1,000 kilometers. The number deserves a moment of stillness. It means that a sound of sufficient energy generated in one part of the ocean at this frequency could in principle be detected on the other side of an ocean basin by a sensitive instrument, its energy degraded by the medium only to the degree that a candle flame is dimmed by a thin cloth placed before it. The ocean, at these frequencies, is not a barrier to sound. It is barely even a filter. 20 hertz sits at or below the lower edge of what most human ears can detect. A person standing in a room where a 20 hertz sound was playing might feel it more than hear it, a pressure in the chest, a low unease, a vibration in the sternum that seems to have no source. The sound would not resolve into a tone. It would be more like a weather condition than a note. And its wavelength in water, the distance from one compression peak to the next, would be roughly 74 meters, longer than most buildings are tall, longer than any ship most people have ever boarded. A single cycle of that wave, stretching through the dark water, would span a distance the eye cannot take in from a single vantage point on land. At that scale, obstacles simply cease to matter. A sound wave diffracts around anything smaller than itself, bends, fills in behind, continues on the other side, as though the object were barely a disturbance. A wave 74 meters long moves around seamounts, through the gaps between islands, past the trailing edges of continental shelves, without breaking or scattering in any significant way. The deep ocean, to a sound at this frequency, is essentially unobstructed, but even within the ocean, not all paths are equal. Sound moves differently at different depths, and this is because the ocean is not a uniform medium. It is layered. Its temperature, its saltiness, its pressure all change with depth, and each of those changes shifts the speed of sound by a measurable amount. Temperature has the strongest effect in the upper ocean. Warm water near the surface allows sound to travel faster than the cold water beneath it. A degree or two of warming changes the sound speed measurably. In the tropical and temperate ocean, the surface layer heated by the sun, mixed by the wind, may carry temperatures of 20 degrees Celsius, or warmer. Below it, the temperature drops, sometimes steeply, through a layer called the thermocline. By the time the water reaches depths of 1,000 meters or more, it is very close to 2 or 3 degrees. Cold, the way the inside of a stone is cold, steady and ancient, and slow to change with anything happening at the surface above. Pressure works in the opposite direction. The deeper the water, the greater the weight pressing down on it, and this compression actually speeds sound up. Below the thermocline, where temperature has stopped dropping significantly, the ever-increasing pressure begins to dominate. Sound speeds up again with depth. The result is a shape. Sound velocity, plotted against depth, traces a curve that descends through the warm upper ocean, passes through a minimum somewhere in the middle depths, typically between 600 and 1,200 meters, depending on the latitude, and then rises again below that. At the top of the curve, the water is warm and fast, At the bottom, the water is cold but compressed and fast. At the minimum, the water is cold and not yet compressed enough to compensate, and sound moves more slowly there than anywhere else in the column. This minimum is the most consequential feature of the acoustic ocean. A sound ray that enters this zone of slow velocity from above or below is bent back toward it, the way light is bent toward a denser medium. It descends slightly too far, and the increasing pressure below bends it upward again. It rises slightly too high, and the warming water above bends it downward. It never escapes. It traces a long, slow sinusoidal path through the water, curving gently up and curving gently down, never touching the seafloor, never reaching the surface, traveling forward through the dark, while the world above continues its ordinary business of weather and light and ships and storms. The relationship between sound speed and these three variables, temperature, salinity, and pressure, has been measured and refined over many decades. Oceanographers and acoustic physicists developed precise empirical equations to describe it, equations tested against measured data from thousands of ocean profiles around the world. One set of equations, developed by Kenneth Mackenzie in 1981, captures most of the variation with reasonable accuracy for ordinary oceanic conditions. Another, from Vito del Grosso, is more precise under the extreme pressures of very deep water, where small errors in the relationship can accumulate over great distances. These equations are not simple. They contain terms and cross-terms and correction factors that reflect the genuine complexity of a fluid medium that varies across 3 dimensions and is never truly at rest. But for the listener resting in the dark, what matters is not the equations. What matters is the shape they describe. A column of water from surface to floor, with sound moving at different speeds at every depth, each layer subtly bending any acoustic energy that passes through it, all of them together producing the geometry of the deep ocean's acoustic life. Sound enters this column from whatever source produced it, and then the ocean begins to work on it. A pressure wave moving through deep water expands outward in 3 dimensions from its source, spreading like a slow sphere of compressed and rarefied water moving away at just over 1,500 meters per second in every direction simultaneously. This spreading alone, the simple geometry of energy being distributed across an ever larger surface, causes the intensity at any given point to fall off with distance. Double the distance, and the same energy is spread over 4 times the area. Triple the distance, and it covers 9 times as much. This is called spherical spreading, and in an unbounded uniform medium, it would govern how quickly a sound fades. But the ocean is not unbounded. It is a layer bounded above by the surface and below by the seafloor. And within its depth, the variation of sound velocity with depth introduces refraction, bending, channeling. Energy that might have spread upward toward the surface and been lost is instead bent back inward. Energy that might have driven down toward the seafloor and scattered against the rough rock and sediment is instead returned toward the middle depths. The geometry of spreading shifts from 3-dimensional to something closer to 2-dimensional. Energy spreading outward in a ring rather than a sphere, covering a surface that grows in proportion to distance rather than distance squared. This is a substantial difference. In spherical spreading, a sound 10 times the original distance has 1/100th the intensity. In the channeled, 2-dimensional spreading of the deep ocean, the same sound at 10 times the distance has only 1/10th the intensity. The ocean's structure preserves acoustic energy across distances that would be impossible in a uniform medium. The measurement of underwater sound uses a different reference than the measurement of sound in air, and it is worth pausing here to understand why. In air, the standard reference for sound pressure levels is 20 micropascals, chosen because it corresponds roughly to the threshold of human hearing at 1 kilohertz. Underwater acoustics uses a different reference, 1 micropascal. This choice reflects the practical reality that underwater sound involves much higher pressures than airborne sound at the equivalent perceptual intensity, and calibrating instruments to the same reference that works in air would produce numbers that carry little intuitive meaning in the ocean context. When underwater source levels are quoted in decibels real 1 micropascal, the numbers are large, sources in the high hundreds, because the scale is calibrated to the extreme pressures that water with its density and stiffness can sustain and transmit. A decibel is itself a ratio, not a fixed quantity. It measures how much more or less energy is present compared to the reference expressed on a logarithmic scale. 10 decibels is a tenfold increase in intensity. 20 decibels is a hundredfold increase. 30 decibels is a thousandfold increase. The logarithmic character of the scale is not a convenience for physicists. It reflects something real about how sound energy behaves over the vast ranges of intensity that matter in ocean acoustics. From the faint signals that arrive after crossing a basin to the intense pressure waves generated by large sources close at hand, and across those vast ranges, seawater absorbs almost nothing from the sounds it carries at low frequencies. The absorption of sound in water arises from several physical processes. Some of it comes from the viscosity of the fluid, the internal friction of water resisting the rapid back and forth motion of a pressure wave. At high frequencies, this process becomes important, and it grows with the square of frequency, meaning that a sound at 10 times the frequency loses 100 times as much energy per unit distance to viscosity alone. Some absorption comes from the relaxation of dissolved molecules. Boric acid and magnesium sulfate are the main contributors at different frequency ranges, which absorb acoustic energy as they shift between molecular configurations in response to pressure changes, then release it a fraction of a second too late, as heat rather than as useful acoustic pressure. At very low frequencies below 100 Hz, and especially around 20 Hz, all of these processes become nearly irrelevant. The molecules do not have time to respond in the wrong way. The viscous losses are tiny. The chemistry of relaxation operates on timescales that are short compared to the period of the wave. The result is that a 20 Hz sound passes through seawater with almost no resistance. The ocean is transparent to it. The medium that is almost everywhere a filter that strips energy from sounds at higher frequencies kilometer by kilometer offers at 20 Hz something close to an open path. The pulse moves forward. In a single second, it covers 1,500 meters. In a minute, it has traveled nearly 60 miles. In an hour, it has moved far enough to be beyond the horizon from any vantage point on the surface above it. In a day, it has crossed a distance greater than most rivers run from their headwaters to the sea. And in that distance, the cold water has taken from it only what the cold water always takes, something very close to nothing. The surface above is untouched. There is no evidence at the surface that anything below is moving. A ship crossing the path of this pulse would detect nothing. The crew would feel nothing. The water at the hull would be the same temperature, the same color, the same salt content as the water anywhere else. The event moving through the deep ocean is invisible, unfelt, unheard by any ordinary means. A pressure wave in the dark, carrying energy across distances that are difficult to hold in mind all at once, losing almost none of it to the water, preserved by the very properties of the medium itself. This is the foundation of everything the ocean does with sound, not the biology of it, not the behavior or the communication or the meaning. Those come from the animals that have lived in this medium long enough to learn its properties intimately. This is the physics beneath all of that. The physics of a fluid under pressure, warm near the surface and cold below, stiff enough to carry a pressure wave at speeds that make a rifle shot seem leisurely, transparent to the lowest frequencies, reflective at its upper boundary, layered in ways that channel and preserve acoustic energy across distances that would defeat any comparable signal in any other medium on the surface of this planet. The ocean's acoustic properties did not develop for any purpose. They are not designed to be a highway for sound, not built to serve the animals that use them. They arise from what water is, its molecular bonds, its response to temperature and pressure, and the dissolved salt that the continents and seafloors have been contributing to it since rain first fell on rock. The properties were there long before there were any ears to perceive them. They will be there long after. They belong to the physics of the planet, not to the biology of the things that live within it. What lives within it has simply found these properties over millions of years and built its acoustic life around them. A pulse of sound leaving a source in the deep ocean expands outward through water that will carry it for distances that are difficult to walk in a lifetime, losing only fractions of a decibel over each 1,000 kilometers to the water itself. The surface above mirrors it back. The floor below reflects it up. The layered structure of the water column bends it, guides it, holds it in the depths where spreading losses are minimized. And the very low frequency of the right sounds passes through all of it, as though the ocean and the signal were made for each other, as though in the long, slow evolution of the ocean and its chemistry, something had been left ready for exactly this. There is a particular quality to the silence of deep water. It is not empty. Low-frequency sound at ocean depths is never entirely absent. There is always some energy present, arriving from distant sources, propagating across the basin from causes too far away to identify by ordinary means. But it is a vast, cold, dark medium in which the pressure of 200 atmospheres presses in from all sides equally, in which the temperature has not changed in 1,000 years, in which the nearest surface is half a mile above, and the nearest floor is half a mile below. In this space, a pulse of energy moving at 1,500 meters per second is the most dynamic thing present. Everything else is still. The stillness is not an absence, it is a kind of density. The water pressing in from all sides is always there, always constant, always moving sound through itself at the same extraordinary speed, always absorbing almost nothing from the signals that trust it with their energy. It is a medium that has been at this for longer than there have been any animals capable of noticing. It will continue long after any such animals are gone. A pressure wave enters the water from above, a raindrop, a breaking wave, a hull, and crosses the boundary into this other world where everything that happens to sound happens differently. The wave does not know this. It has no knowledge and no intention, only energy and direction and the properties of the medium around it. It moves forward at 1,500 meters per second through the cold and the pressure and the dark, the ocean giving it back almost everything it asks of it, holding its energy inside the great dense world of the water rather than releasing it to the thin air above. And the pulse moves outward, far from its source now, at distances that have no comparison in ordinary terrestrial life. 100 kilometers, 200, 500, 1,000, still carrying most of the energy it began with, still moving at the same speed, still tracing the same long, slow sinusoidal path through the water column, guided by the same gradients that guided it from the first moment it entered the sea. The ocean behind it has changed nothing. The ocean ahead of it will offer nothing different. Cold water, high pressure, near zero absorption, the surface above acting as a seal, the structure of the medium itself holding the sound in the world below. The pulse is still moving. It will continue to move through the dark and the cold, and the pressure for as long as the ocean holds it, and the ocean is very good at holding. It does not forget what it is given. The energy that entered at one point continues forward through the vast interior of the sea, smaller now with distance, thinned by the geometry of spreading, but still present, still coherent, still carrying within its frequency content and its pressure amplitude the signature of its origin, a signal crossing an ocean, losing almost nothing to the water, only spread, only distance, only the patient arithmetic of waves expanding outward through the most extraordinary acoustic medium on the surface of this planet. And somewhere in the deep, the water that has always been cold and always been dark and always been still receives this pulse as it has received every pressure wave that has ever passed through it, without awareness, without preference, without memory, only with the properties that physics gave it when the planet cooled and the oceans formed and the rain began to fall. The pulse moves on, and the water holds it, and the quiet of the deep persists all around it, undisturbed. 800 meters below the surface of the North Atlantic, where the last trace of any light from above has long since been absorbed, the water is very still. No wave reaches this depth. No wind shapes anything here. The pressure at this depth presses in from every direction with a weight that would collapse most living structures in seconds, and the temperature hovers just above 2 degrees. Cold enough to slow nearly every chemical process, cold enough to make the water dense and heavy and very, very quiet, or so it seems. The silence here is not true silence. It never was. A sound descends through the upper ocean and slows as it goes. In the warm water near the surface, it moves quickly, pulled along by the heat that loosens the water's internal bonds and allows pressure waves to travel fast. But as the sound sinks deeper, the temperature falls. The water cools through the upper few hundred meters, and that cooling slows the sound measurably, degree by degree, meter by meter. The wave of compression that was racing near 1,500 meters per second begins to ease. It loses speed the way any traveler loses speed when the road becomes harder, and it keeps descending, still slowing, into the cold and the dark. There is a depth where the sound moves more slowly than it does anywhere else in the ocean. Not dramatically, not suddenly. The change is gradual and continuous, like the change in light between afternoon and dusk. But at a certain depth, the slowing reaches its limit. Below that depth, something different begins to take over. The water is still cold, but now the weight of the ocean above becomes the dominant force. Pressure builds with every additional meter of depth, and pressure compresses the water slightly, making it fractionally stiffer, and stiffer water transmits sound fractionally faster. So below that critical depth, the sound's speed begins to rise again. It accelerates slowly, pressed forward by the weight of the ocean above. This means there is a layer, a thin horizontal band of ocean suspended hundreds of meters down, where sound moves more slowly than anywhere above it, and more slowly than anywhere below it. It is a valley of velocity, measured not in stone and soil, but in the acoustic properties of cold salt water. And a valley for sound is a trap, When sound travels through a medium where its speed varies, the sound bends. It bends the way light bends when it passes from air into glass, not because any force is pushing it sideways, but because one side of the wave is moving faster than the other, and the whole wave swings toward the slower side. Sound moving downward through the thermocline, slowing as it goes, bends downward. Sound moving upward from the cold deep, speeding up as it rises, bends upward. And sound that reaches the velocity minimum from either direction finds itself turned back, curved gently back toward the depth where it started, the depth where velocity is lowest and the tendency to bend is strongest. The sound does not bounce. It does not reflect off a hard surface. It curves. It follows a long, slow arc through the water, upward from the valley axis, bending over, coming back down, passing through the axis again, continuing below, bending back upward. Over thousands of kilometers, a single pulse traces a sinusoidal path through the deep ocean, rising and falling in gentle arcs, never quite reaching the turbulent surface above, and never quite touching the absorbing sediment below. It is held between them. It is held in the valley. This layer is called the SOFAR channel. The name comes from the letters of the longer phrase, sound fixing and ranging. It forms at depths of roughly 600 to 1200 meters in the tropics and the temperate ocean, shallower where the surface water is cold, deeper where it is warm, sometimes reaching all the way to the surface, near the poles where the surface itself is already cold enough to sit at the channel's axis. In most of the open ocean, it sits quietly in the dark, invisible to anything swimming through it, unremarkable in every sense that a living creature might use to navigate. There is no current here, no chemical gradient, no change in color or texture. The water at the SOFAR axis is indistinguishable from the water 100 meters above or below it, except in one property alone, the speed at which it carries sound, and that single property changes everything for a low-frequency sound that has found its way inside. Imagine the upper ocean as a place of loss. Near the surface, waves break and trap bubbles. The bubble-laden water near the sea surface scatters sound, reflecting it in many directions at once, absorbing a small fraction of its energy with each reflection. Storms roughen the surface and deepen the bubble layer. In shallow water, sound bounces repeatedly between the surface and the seafloor, losing a little energy with every bounce. The seafloor is not a perfect mirror. It is sediment and rock, and it absorbs. The sea surface absorbs less, but it scatters. A sound trapped near the surface in shallow water will travel a few tens of kilometers before it has lost too much energy to be useful. The SOFAR channel removes these losses almost entirely. A sound inside the channel never touches the surface. It never touches the seafloor. It travels its arcing path through open water, losing energy only to the water itself, and water, for low-frequency sound, is an extraordinarily reluctant absorber. The energy in a long, slow pressure wave at low frequency passes through seawater with almost nothing taken from it. What the channel adds to this is geometry. Instead of spreading outward in 3 dimensions equally, losing intensity as the wavefront grows, sound inside the channel is partly constrained. It spreads primarily in 2 dimensions, along the surface of the waveguide, rather than into the full sphere of open water. The wavefront grows more slowly. The energy is less diluted. The result is propagation over distances that seem at first encounter to belong to a different kind of physics. A sound launched from the middle of the North Atlantic at the right depth and at the right frequency can propagate to the far side of the ocean, not diminished to a whisper, not absorbed by thousands of kilometers of water, but arriving after that crossing as something still measurable, something still above the threshold of detection. The ocean does not give this freely or to all sounds equally. It gives it to sounds that fit the geometry of the channel, that match the wavelengths and frequencies the channel is sized to carry. It gives it most generously of all to sounds of very low frequency, long, slow waves that bend smoothly around any obstacle smaller than themselves, that pass through the water with minimal absorption, that travel inside the sinusoidal path the channel offers without leaking out. The thermocline plays a particular role in this. Between the warm surface layer and the cold deep ocean, temperature drops steeply from surface values that might sit above 20 degrees in the tropics, falling through a few hundred meters, to values close to 2 or 3 degrees at depth. This steep gradient refracts sound strongly. A ray traveling upward from the SOFAR axis, angling toward the surface, passes through the thermocline and bends back downward before it ever reaches the bubble-filled zone near the surface. The thermocline acts as a ceiling, not hard and reflective, but soft and refractive, turning sound back into the channel before it can reach the surface. Losses above, the sound never quite arrives. It curves away. Below the axis, the increasing pressure turns rays back upward before they reach the sediment, and so the sound travels between these two soft boundaries, the thermocline above, the pressure gradient below, for as long as the ocean continues, for as many thousands of kilometers as the channel extends. The channel extends very far. It runs across every major ocean basin, in the Atlantic, the Pacific, the Indian Ocean, wherever the deep water is deep enough and the surface warm enough to create the necessary velocity structure, the channel exists. It is not a narrow tube. It is a horizontal plane of influence, hundreds of meters thick, spanning entire basins. Sound inside it does not travel in a single straight line. It fans outward in all directions simultaneously, each ray following its own sinusoidal arc, the whole pattern expanding like a slow, invisible ring from its source point at the axis. Within the channel, the physics of propagation can be described in more than one way. One way treats sound as a collection of rays, each bending according to the local velocity gradient, the picture built from geometry, each path calculable if the velocity profile is known. Another way treats the channel as a waveguide, a constrained acoustic space in which the sound field is built from a set of patterns, modes, each one a distinct interference structure, each one traveling across the basin at a slightly different speed. The modes disperse as they travel. The fast modes arrive at a distant receiver before the slow ones. Over thousands of kilometers, what began as a single brief pulse at the source spreads into a long, complex arrival pattern, a dispersed signal that carries, encoded in its structure, information about the distance and depth of the source, and about every variation in the channel through which it traveled. These are not the same modes that carry humpback song. The modes of the SOFAR channel are shaped by the whole depth structure of the ocean, the temperature, the salinity, the pressure at every depth from surface to floor. They are large-scale features of the acoustic field, each one occupying the full depth of the waveguide. A signal traveling thousands of kilometers arrives as a sequence of these modes, lowest order first, dispersed over many minutes of real time. Oceanographers reading the arrival pattern can reconstruct something of the channel's internal structure from it. The signal carries its own history. Sound also travels through the SOFAR channel in a way that creates what are called convergence zones, regions on the surface, at intervals of roughly 50 to 80 miles apart, where refracted rays from below arrive together and produce a localized region of elevated sound intensity. Between these zones, the signal is much weaker. A source at depth is heard loudly at a convergence zone, more faintly in between, loudly again at the next convergence zone beyond. This creates a kind of acoustic geography on the ocean surface, alternating regions of clarity and shadow, spaced regularly, crossing the whole basin. The channel itself is not identical everywhere. Temperature and salinity vary across the ocean, with latitude, with season, with the circulation patterns that carry warm and cold water around the basins. The depth of the axis shifts. In tropical waters, it sits deeper. Near the poles, it rises toward the surface, and in some high-latitude regions, it effectively disappears as the surface water becomes cold enough to merge with the deep water's temperature structure. Seasonal changes in surface temperature move the thermocline up and down, altering the upper boundary of the channel. The channel breathes with the seasons, though slowly, over months rather than days. Sound entering the channel from outside, from above, from a source too shallow to sit directly at the axis, does not stay within it as efficiently as sound launched from the axis itself. Some energy escapes upward or is lost to the surface. The coupling between a surface source and the deep channel is imperfect. A source at the axis injects its energy directly into the most efficient propagation path. A source far above the axis contributes some energy to the channel and loses some to the poorly coupled upper ocean. The geometry of source depth, in other words, matters enormously for how far a signal carries. All of this was understood to some degree by the physicists who studied underwater acoustics in the middle of the 20th century. The mathematics of sound propagation in layered media had been worked out. The principles of refraction were clear. What was needed was proof, an experiment that could demonstrate unambiguously that the ocean could carry a sound signal across a full ocean basin without losing it entirely. Two scientists named Maurice Ewing and J. Lamar Wurzel provided that proof in the years just after the Second World War. Ewing was a geophysicist who had spent years thinking about sound propagation in the ocean, studying sediment structures, using explosive charges detonated in the water, and listening to the echoes from below. He understood the velocity structure of the deep ocean better than almost anyone of his time, and he recognized that the velocity minimum at depth implied something profound, a natural waveguide, built into the ocean itself, capable of channeling acoustic energy across distances far greater than anyone had demonstrated. Wurzel was a younger colleague, working with Ewing at Columbia University. Together, they designed a set of experiments that were elegantly simple in principle, if not in execution. They would detonate small explosive charges at depth in the Atlantic Ocean, small enough not to be dangerous, large enough to produce a detectable signal, and they would place hydrophones at distant shore stations to listen for the arrivals. The explosions were set off in the deep water of the Atlantic, small charges, carefully positioned to release their energy near the depth of the velocity minimum, sent pulses of sound into the channel, and at shore stations far away, hundreds of miles, then more, the hydrophones waited. The signals arrived, not as a brief crack, but as a prolonged sequence of arrivals, drawn out over minutes as the different modes and ray paths reached the receivers at different times. The same explosion, the same pressure wave, detected intact across the ocean. The same event arriving at multiple stations simultaneously, its travel time carrying the distance, its dispersed arrival pattern carrying the geometry of the channel through which it had passed. What Ewing and Wurzel had confirmed was not something they had invented. The channel had been there, carrying sound across the ocean for as long as the deep ocean had existed in anything like its present form, long before any hydrophone was lowered to depth, long before any mathematician derived the equations of mode propagation in a layered waveguide. The channel had been doing what it does, collecting low-frequency sound at depth, curving it back toward the axis when it tried to escape, carrying it outward across the basin with a patience that required no mechanism more complex than the simple relationship between temperature and the speed of sound. The ocean had always known how to do this. No one had asked it to. In the years that followed, as the physics of the channel became well established, it found a new purpose, or rather human technology found it. The Cold War brought with it a powerful interest in detecting sounds at great distance across the ocean. A network of hydrophones was built and deployed across the Atlantic and Pacific Oceans, each station connected by cable to shore facilities, each one listening continuously to the low-frequency sounds that the channel carried. The network was built to detect the sounds of submarines. It was exquisitely sensitive, calibrated to the exact frequency range that the channel carried most efficiently, placed at depths near the SOFAR axis, listening at all hours of every day and night across every season. What it heard was not only submarines. It heard earthquakes, their seismic signals converted to pressure waves at the ocean floor and channeled for thousands of miles. It heard the impacts of meteorites striking the ocean. It heard the low rumble of distant volcanoes erupting beneath the sea surface. It heard ice calving from glaciers in the far north and south, the massive acoustic events of collapsing ice shelves translated into low-frequency pulses that traveled into the channel and crossed entire basins before arriving at hydrophones far away. The ocean, the instruments found, was not quiet at all. At low frequencies, it was full of signals, ancient, continuous, deeply geological, and it heard something else entirely. The signals appeared in the records as slow, repetitive patterns of low frequency, not the sharp, impulsive signature of an explosion or an earthquake, but something more gradual, more structured, returning at intervals that suggested rhythm rather than geology. The patterns were consistent across days and weeks. They appeared in season. They came from points in the open ocean, not from the seafloor, not from any fixed geological feature. The hydrophones could triangulate the positions of these sources, and the positions moved, slowly, over hours and days, following paths through the open water. The technology built to detect the sounds of submarines had detected the sounds of animals. Animals whose calls were so low in frequency that they fitted almost perfectly into the channel's most efficient propagation band. Animals whose source levels were high enough that the channel could carry their calls across distances that no one had imagined any biological sound source could achieve. Animals that had, it turned out, been using the SOFAR channel for far longer than any human engineer had known it existed. The whale calls in those records were not artifacts. They were not noise. They were structured, repeating, population-specific signals, calls that had evolved over millions of years of selective pressure in the deep ocean to fit precisely into the acoustic environment that the SOFAR channel provides. Whether this was the result of direct selection for long-range propagation, whether the channel shaped the evolution of the calls themselves, is a question without a clean answer. But the fit between the calls and the channel is not coincidental, and it is not small. It is as close as any biological structure and its environment come to matching. Below the surface, in the dark of the Middle Atlantic at depth, the channel carries on as it always has. A pressure pulse enters it from somewhere in the open water. The source is a living thing, warm-blooded, breathing air, existing at the surface for long enough to take breath before descending again into the cold. Its call is low, far below what most ears register as sound. The wave that leaves its body is slow and long, each cycle taking a full second, stretching across a distance far greater than the animal itself. The wave reaches the depth of the SOFAR axis and is not lost, it is held. The thermocline turns it back when it tries to rise. The pressure gradient turns it back when it tries to descend, and so it travels horizontally in the only direction the channel easily permits, outward, across the ocean, losing almost nothing to the water through which it passes, carrying its full structure intact. Hours pass. The pulse has now traveled several hundred miles. The animal that made it has long since surfaced, breathed, perhaps surfaced again, moved on through the water at a few miles per hour in whatever direction the season and the feeding require. The call continues without it. The sound and the body that made it have parted company entirely, the one remaining fixed in the physics of the channel, the other moving through the surface world as living things must. More hours pass. The pulse approaches a far coastline, where the ocean shallows and the SOFAR channel loses its geometry, the rising seafloor cutting through the axis from below, the warm surface water thinning above. The channel frays at the edges. The sound scatters into the shallower water, reflects off the bottom, loses coherence. What arrives is no longer the clean, structured signal that left the deep ocean hundreds of miles away, but it arrives. Something of the original pulse survives, attenuated and dispersed, but above the threshold of the instruments waiting to receive it. Across the whole width of the open ocean, the channel kept its hold. The valley of velocity continues to exist, as it has for millions of years, deep, cold, unreachable by any ordinary storm, indifferent to the seasons playing out above it. Sound falls into it, and the valley holds the sound. The sound travels, and far away, at another depth, at another point in the great dark water of the ocean basin, the pressure wave arrives, small, changed by its long passage, but present. The ocean, it turned out, had built a listening system long before anyone thought to build one. Ewing and Wurzel confirmed in one ocean what the deep water had been doing in all of them, without announcement and without end. A signal crosses the Atlantic, the instruments record it, and somewhere in the slow, continuous record of a hydrophone suspended at depth in the dark, the same ancient physics writes itself out again. The same valley, the same curve of refraction, the same holding of a wave across the basin's full width. The water at 800 meters is still and cold and dark. No current moves through it that a swimmer would feel. No light touches it. The pressure is steady and immense in every direction. And through it, at this moment and every moment, low-frequency sound is passing, crossing from somewhere to somewhere else, following the slow sinusoid of the channel's geometry, losing almost nothing, carrying whatever it carries, arriving wherever it arrives. The ocean was always doing this. No one needed to tell it how. 20 hertz, a single cycle of compression and rarefaction, stretching through cold seawater for 74 meters before it completes itself. Longer than a city bus, longer than most buildings are tall, a wavelength so large that it could swallow the whole body of the animal that made it and still have room to spare. That is where the blue whale's voice lives. Not in the range a human body can resolve, but far below it in a register felt through bone and water before it is ever understood as sound. The frequency is not an abstraction. It is a physical dimension. A single wave of that pitch, crossing open ocean, occupies the length of a sprint distance, end to end, before the next wave begins. The animal that produces it is traveling somewhere in the dark water below the thermocline. It makes no sound audible to any nearby swimmer. The ocean above it is moving with weather, with current, with the distant collision of waves against distant shore. None of that reaches the animal. None of it interrupts the slow, steady production of something so low in pitch that it belongs to a different part of physics than conversation, than music, than the range of sounds any human ear was built to catch. The call expands outward through the surrounding water at close to 1,500 meters per second. It passes through the body of the ocean with almost no resistance, and it travels. The blue whale's voice begins near or below the lowest limit of what a human ear can detect. 20 hertz sits right at that threshold, and the sounds blue whales produce are often at or beneath it. In a room, a person standing close to a large speaker driven to that frequency would feel it in the sternum, the jaw, the soles of the feet, not hear it exactly, but feel the air itself moving against the skin. In water, at the pressures and densities of the open ocean, the same frequency propagates with far less loss, far greater efficiency, across distances that make a room seem too small to think about. A source level of 188 decibels measured in water, reference to 1 micropascal at a distance of 1 meter. That number resists easy comparison to human experience because the reference unit for sound in water differs from the one used in air. But in terms of the pressure wave itself, the amplitude of the compression and rarefaction moving outward from the animal's body, it places the blue whale among the loudest acoustic sources in the ocean. Not loud in the way a sound feels loud to a body standing in a room. Loud in the sense that the energy broadcast with each call is enough to propagate for hundreds, and under the right conditions for thousands, of kilometers before it falls below the ocean's own background noise. The whale does not open its mouth to produce this sound. It does not exhale. Deep in the larynx there is a structure, a fold of tissue arranged in a U shape, and air moves through it or around it in a way that is not yet fully resolved by the biologists who study it. What appears to be happening is that air is recycled, moved through the vocal apparatus without being released into the surrounding water, so that a whale, hundreds of meters below the surface, can sustain phonation for many minutes without depleting the air it will need when it rises. The sound is generated internally, without a breath leaving the body. The ocean beyond the animal's skin receives only the wave, not the air. Each call is not a single burst, but a structured unit. Blue whale calls last roughly 10 to 30 seconds, depending on the population. They repeat, one unit, then a pause, then another, with the interval between them as consistent and recognizable as the call itself. A recording made over the course of a night might capture dozens of these units, each one nearly identical to the last, tiling across hours of time like the slow measured beat of something very large and very patient. A blue whale, resting at depth, produces these calls in a rhythm so consistent that the interval between units can be used to identify individual animals in a long recording, not because individual whales have unique voices in the way individual humans have unique voices, but because the calls of blue whales carry the acoustic identity of their population in the shape and timing of each unit. A call recorded in the Indian Ocean carries different spectral characteristics than a call recorded off the coast of California. The frequency contour of one population's call slopes in a direction the others does not. The duration of the tonal elements differs. The spacing between units differs. These are not random variations. They are stable, consistent, inherited at the population level. A dialect laid down not in the neural architecture of a single animal, but in the collective acoustic behavior of a group. The dialect crosses entire ocean basins and arrives intact. A hydrophone on the floor of the ocean, receiving signals from many directions at once, can distinguish a call produced by whales from the eastern North Pacific from a call produced by whales in the central Indian Ocean. The call shape survives propagation distances of 2,000 kilometers or more, with enough of its structure preserved that the population of origin can still be read out of the received signal. Not perfectly, the ocean absorbs and refracts and spreads the energy as it travels, but well enough that the acoustic fingerprint of a population remains legible across the width of an ocean basin. Consider what that means for an animal navigating waters that contain others of its kind. A blue whale approaching a feeding ground in late summer or crossing toward a breeding area as the water cools produces calls that announce not only its presence, but its origin. Others receiving that signal across hundreds of kilometers are not receiving a uniform, generic tone. They are receiving something specific, something that places the caller in a particular lineage, a particular tradition of sound making that persists across generations. The fin whale produces a similar kind of call, also near 20 hertz, also infrasonic, also well matched to the physics of deep ocean propagation. It is worth dwelling on what the fin whale represents acoustically, because it sits at a scale that the mind resists fully absorbing. Fin whales are the second largest animals on Earth. Adults can reach close to 90 feet in length, and their mass, their sheer displaced volume in the water, makes them among the largest forms of life this planet has produced in the last several 100 million years. A fin whale moving through the ocean does so with a slowness and deliberateness that comes not from any lack of capacity, but from the immense inertia of a body that size. That animal produces calls estimated at up to 189 decibels, reference to 1 micropascal at 1 meter, among the highest source levels ever measured from a living organism. Not a brief explosive sound, but a 1-second pulse, tonal and precise, delivered in a pattern that repeats across hours. The fin whale's pattern is a doublet, 2 pulses, delivered one after the other, separated by an interval that varies between roughly 7 and 37 seconds, depending on the individual and the context. 2 marks on a spectrogram, separated by silence, then the same pair again and again, repeating over the span of hours, consistent in their timing, consistent in their frequency, drifting slowly through the deep water of the open ocean in all directions at once. At a distance, at the scale of hundreds of kilometers, the doublet remains recognizable. The pause between the 2 pulses within a pair is shorter than the pause between successive pairs, and that architecture survives propagation. The receiving ear, biological or electronic, can count the interval, identify the structure, and know the call for what it is. The pulse itself is close to 1 second in duration. It is centered near 20 hertz, though fin whale calls in different ocean regions carry slightly different center frequencies. Like blue whale populations, fin whale populations appear to produce calls with locally consistent spectral characteristics. The same mechanism, a stable, inherited population-level acoustic pattern, persisting across generations, carrying information about origin in the shape of the signal. What information that carries to other fin whales and how it is used remains an open question. The behavioral functions of these calls have not been fully resolved. Calling rates rise in autumn and winter and fall in summer, a pattern consistent with social or reproductive communication rather than navigation or feeding. Fin whales call most intensively at the times of year associated with movement toward breeding areas, and with the concentration of animals in overlapping ranges. Whether the calls attract other individuals, establish acoustic presence across a territory too large for any animal to physically patrol, or serve some function not yet identified, none of this is certain. What is certain is the physics. The call is generated, the energy propagates, the ocean carries it. A fin whale producing that doublet on the surface of a winter Atlantic, calling through the long dark of the season at full rate, is broadcasting its presence across a distance measured not in miles but in ocean widths. The pulse travels into the thermocline and through it, descending toward the depth where temperature stops driving sound speed and pressure takes over, where the minimum velocity layer holds acoustic energy in its slow-moving core and carries it forward. The doublet, produced once, can be received by any sufficiently sensitive ear or instrument over a range that in some conditions extends to thousands of kilometers. Blue whales and fin whales are not the only baleen whales with voices near this frequency, but they are the most extensively studied, the best understood in terms of call structure and propagation, and in terms of source level, they are the loudest. The physics of their sound making is closely matched to the physics of the medium they inhabit. The wavelength of a 20 Hz call is large enough to diffract smoothly around almost any obstacle in the ocean, a seamount, a ridge, the broad curve of a continental shelf, the way a wave wraps around the end of a breakwater. The call does not need a clear line of sight to its destination. It bends around what stands between. At lower frequencies, the ocean absorbs very little. A signal near 20 Hz traveling through deep, cold seawater loses approximately 1/10 of a decibel over 1,000 kilometers to absorption alone, 1/10 less than the variation produced by minor differences in ocean temperature. The call that leaves an animal at full source level arrives at a receiver 1,000 kilometers away, with nearly all its original energy still present, diminished only by the geometric spreading of the wavefront as it expands, and by whatever small fraction of it the water has converted to heat along the way. That geometrical spreading matters, and it is worth understanding slowly. As a sound wave expands outward from its source, the same energy covers a larger and larger area of the wavefront. Double the distance, and the same energy is spread over 4 times the area. The intensity at any receiving point falls as the square of the distance in open water in 3-dimensional space. In the SOFAR channel, propagation is more constrained, more nearly 2-dimensional in some regimes, and spreading is less severe. Energy that would dissipate rapidly in open air or in water with no waveguide stays concentrated in a layer. The same amount of energy guided forward rather than allowed to bloom outward in all directions equally. This is what the channel does. It holds the sound, and the ocean's exceptional transparency at low frequencies means that even the held sound, spreading cylindrically rather than spherically across thousands of kilometers, retains enough amplitude to be detected. The blue whale at 20 Hz and the fin whale in its close neighborhood of that frequency evolved voices in a register that the ocean cannot easily diminish. Whether that match was gradual, driven by the differential survival of animals whose calls reached farthest, or whether it reflects some other mechanism, the answer is not available. What remains is the correspondence between the physics of the medium and the acoustic output of the animals living in it, a correspondence so precise it is difficult to look past. A blue whale call produced at the surface of the South Atlantic in early winter will, under favorable conditions, reach a receiving ear in the North Atlantic many hours later. The sound travels at close to 1,500 meters per second. 1,000 kilometers takes roughly 11 minutes. 2,000 kilometers takes a little more than 20. The call does not wait. It does not hesitate at the boundary between warm and cold water, between one ocean basin and another. It follows the physics. It bends with the gradients. It arrives. The question of what another blue whale does with a received call, how far the detected signal influences the receiving animal's behavior, whether the population dialect information carried in the call is read and acted on, or whether it functions simply as a signal of presence over distance, is not resolved. The acoustic ecology of these animals is understood in outline and not yet in detail. Researchers working with recordings from fixed hydrophone arrays have documented calls being produced across seasons, across regions, across years. They have described the call structure and its geographic variation. The behavioral loop call, receive, respond has been observed in broad terms, but not fully mapped at the individual level, partly because the animals live in a medium that makes direct observation at the scales where these calls operate nearly impossible to achieve. What has been mapped is the sound itself, its structure, its source level, its propagation, its consistency across populations and decades. Blue whale calls recorded in the same ocean region 30 years apart carry the same dialect, the same frequency contours, the same timing architecture. The tradition has held through whatever changes the population has experienced, through decades of ocean warming, through the slow recovery of numbers following the collapse of whaling. The call is older than any individual animal alive today. It is older than the scientists who first recorded it. It persists in the ocean the way a current persists, not in any single molecule of water, but in the pattern those molecules trace together as they move. A blue whale calf in the months after birth is close enough to its mother that the acoustic signal between them is not the 60 decibel, continent-spanning broadcast of a solitary adult. The mother-calf pair exchanges calls at close range, quiet by the standards of open ocean communication, intimate in the sense that they are not meant to cross any great distance. The calf's calls are not yet the precise, stereotyped units of the adult population. They are variable, exploratory, moving toward the form the population carries, but not yet there. The adult call is learned, or perhaps more accurately, it is approached over time, the young animal producing sounds that gradually converge on the population template without any apparent formal teaching. The ocean receives the calf's early calls the same way it receives the adults. The physics does not distinguish. The pressure wave expands outward from the young animal's body into the cold water around it at the same speed, in the same directions, subject to the same gradients and reflections as any other. But the calf's energy output is far lower, and the population-specific structure is not yet fully formed, and no receiving animal, thousands of kilometers away, would recognize the call as carrying the identity of the population. It is a voice finding its shape. The ocean holds it anyway, for whatever brief distance it travels before it falls below the noise floor. Fin whale populations, like blue whale populations, show geographic consistency in their call characteristics. Animals off the coast of Iceland produce doublets that differ measurably from those of fin whales in the Mediterranean or in the North Pacific. The intervals differ. The center frequency differs slightly. The amplitude envelope of the individual pulse carries population-specific characteristics. These are not drastic differences. To a casual observer, one fin whale doublet sounds like another, but to an instrument calibrated for the purpose, or to another fin whale evolved to pay attention to these details, the differences exist and are stable. The mechanism by which young fin whales acquire the call pattern of their population is not known in the same way the mechanism of humpback song learning is known. The fin whale's infrasonic pulse is simpler in structure than humpback song, less obviously a cultural performance, and the evidence for active learning and transmission is less direct. It may be that the call structure is substantially innate, with geographic variation arising through some combination of genetic and developmental factors, rather than through imitation and cultural inheritance. Or learning may play a role not yet measured. The honest answer is that the question is not fully resolved, and the evidence available does not settle it. What is not in question is that the variation exists, that it is geographically consistent, that it has been stable across decades of observation, and that it functions as a reliable acoustic marker of population identity in the received signal. The dark water of the Northern Ocean in late autumn holds these calls in enormous numbers. Blue whales that spent the summer feeding at high latitudes are moving, and they are calling as they move or as they rest in the deep water. Fin whales in their own seasonal rhythms are producing their doublets across broad areas of the North Atlantic and North Pacific simultaneously. The low-frequency soundscape of the ocean in these months, at frequencies near 20 Hz, is threaded through with these signals. Not a cacophony, the calls are spaced in time and spread across space, but a continuous, low, slow presence. A background of infrasonic biology braided through the physical noise of the ocean itself. A hydrophone resting on the seafloor in the mid-Atlantic, recording continuously through those months, captures all of it. The distant thunder of microseisms generated by wave interactions at the sea surface, centered near 1/10 of a hertz, far below the blue whale range, but visible on the same broadband record. The intermittent pulse of a fin whale nearby. The sustained, modulated note of a blue whale call, arriving from a direction the instrument can triangulate, if paired with other instruments in a network. And underneath all of it, the slow, steady ambient background of deep water at low frequency, the hum of an ocean that is never quite silent, never quite still. In that ambient field, the blue whale's call stands out not because it is uniquely loud compared to all the sources in the ocean, but because of its temporal structure. The repeated unit, the consistent interval, the spectral shape centered near 20 Hz, these create a pattern in the noise that a matched filter, biological or electronic, can extract. A receiving whale that has evolved to detect calls with this specific architecture will perceive it at distances far beyond where a naive observer, listening for anything at all, would lose it in the background. The signal-to-noise ratio at the population's call frequency is better than it would be at any other frequency, not only because the ocean propagates that frequency well, but because the receiving animal is listening specifically for it. That specificity, the match between the call's structure and the receiver's tuning, is part of what makes this system function at basin scale. The information in the call does not need to be carried perfectly intact all the way to the receiver. It needs to carry enough structure that the receiver can recognize the template, and because the receiver is not listening at random, but is tuned to the population's call, the effective detection range is extended by the receiver's own acoustic sensitivity. 2,000 kilometers is not a limit. It is a rough middle value for favorable conditions. Under the best conditions, cold, deep, unobstructed water, the call propagating through the minimum velocity layer rather than through the mixed upper ocean, a background noise level low enough for the signal to stand above it, the detection range may be significantly greater. The geometry is favorable. At these frequencies, the ocean is the right medium. The depth channel holds the energy, and the call was made for exactly this. A blue whale producing its call in the deep water of the Indian Ocean, in winter, is present in the acoustic space of the entire basin. Other animals with ears tuned to that frequency and that call structure anywhere within detection range can know that something of their own kind is present somewhere to the north, or south, or east. Not its exact location, a single receiver cannot triangulate, but its presence and, carried in the spectral shape of the call, its population identity. That information crosses the water in 11 minutes per 1,000 kilometers. It arrives before the ocean even has time to change its temperature by a measurable fraction of a degree. The patience of these animals in the deep water, calling through the dark months at regular intervals, is not patience in any human sense. There is no waiting, no hoping, no expectation. There is only the production of sound, and the sound's propagation, and whatever the physics and biology of receiving animals make of the signal when it arrives. But in the slow accumulation of calls across a season, across a basin, across generations of animals, producing the same structured infrasonic broadcast into the same cooperative ocean, something has been maintained. The ocean carries it, the population continues. A call produced once, near the surface of the winter ocean, falls away from the animal that made it and into the water, where it belongs to physics rather than to biology. It crosses the boundary between the warm surface layer and the cooler water below. It descends toward the velocity minimum, bending as the gradients pull it. At the axis of the deep channel, it no longer belongs to one place in the ocean. It belongs to the whole connected space of the basin, propagating forward through the dark, losing very little, carrying the acoustic mark of its origin intact. At 20 hertz, a wavelength of 74 meters folds through that water with no effort. It diffracts around what it meets. It travels forward at 1,500 meters per second through temperatures the human body would not survive, at pressures no unprotected human structure would withstand, through depths where no light has ever arrived from the surface. In that darkness, in that cold, in that perfect acoustic transparency, the signal continues. It does not know where it is going. Nothing has sent it. No intention accompanies it. The water received it, and the water carries it, because these are the rules of water, and at 20 hertz, the ocean is extraordinarily good at following them. Somewhere far ahead, hundreds of kilometers, perhaps more, the pressure wave arrives at another body in the water. It moves through that animal the way it moves through anything that has the density and compressibility of seawater, which is to say, almost without reflection. The call reaches the inner ear of another blue whale, or it passes through, depending on whether that animal is listening. The physics does not require a receiver. The wave exists whether or not any ear is present to resolve it. But in the long history of these animals in this ocean, some of those receivers were present. Some of them were listening. The population's call carried something across the distance between them, and whatever that something was, presence, identity, direction, an answer to a question that takes weeks to ask and months to answer, the ocean delivered it, cold and vast and quiet at the frequencies where human hearing falls away. The deep water holds the calls of blue whales moving through their season. The signals travel outward from each animal in all directions simultaneously, curving slowly in the gradients, finding the channel, spreading forward across the dark. The ocean loses almost nothing of what has been given to it. It holds the sound the way deep water holds temperature, slowly, with enormous capacity, releasing it over distances that make the surface world seem very small and very brief. A pulse leaves a blue whale somewhere in the South Atlantic in the long dark hours before dawn. 74 meters long, close to 20 hertz, carrying the spectral signature of its population, intact and precise, in the shape of the wave itself. The cold water receives it and begins carrying it north. Hours pass. The animal produces another call, and another. Each one enters the ocean and travels. The first pulse is already hundreds of kilometers away by the time the third is made. The water between them holds nothing they would recognize as memory, but the wave itself is real, physical, present in the water column as a measurable fluctuation of pressure, traveling on through the dark at 1,500 meters per second, carrying its origin with it, reaching toward whatever ear or instrument the ocean holds in its path, losing so little to the journey that the arrival is almost as full as the departure. The ocean keeps almost everything. A sound is moving through warm water on a winter afternoon somewhere in the North Atlantic, and a human ear placed directly against the source of it would hear nothing at all. Not silence, the specific, expectant quality of sound, just below what the body can resolve. A pressure wave is expanding outward through the sea in every direction, its wavelength longer than a city block, its frequency so low that the human cochlea, tuned for voices and footsteps and the middle range of the world, passes over it without registering. The wave is there. It is real. It is by any physical measure one of the most energetic sounds in the ocean at this moment. The animal producing it hangs motionless somewhere above the thermocline, and nothing about its posture or its stillness would suggest to a watching eye that anything at all was happening. This is the first thing to understand about humpback whale song. The version a human can actually hear is only part of it. The full structure descends below the threshold of human hearing and climbs well above the middle frequencies of a singing voice. It occupies a range of sound that no other ocean animal covers in quite the same way, reaching from the infrarsonic depths where pressure waves stretch on for dozens of meters before completing a single cycle, up through the registers where dolphins click and children call and the ocean surface hisses with breaking foam. A single theme within the song can span that entire range in the time it takes a person to draw a breath. The lowest frequencies will carry for hundreds of miles. The highest will dissolve into the water within a few kilometers, absorbed by the sea itself. Roger Payne and Scott McVeigh described the architecture of this sound in 1971, and what they found was not noise, not the random acoustic output of a large animal vocalizing in the dark. What they found was structure, deep, nested, consistent structure, organized with a precision that no one had expected, and that has not entirely been explained in the decades since. A sound would form, lasting a second or two or five. That sound was part of a sequence. The sequence was part of a phrase. The phrase was one of several that built a theme, and the theme was one of several that, taken together, constituted the song. The whole thing, theme after theme, each phrase following the last with the orderly patience of something that knows exactly what comes next, could last for half an hour. The same song, every male in the population. That season, not approximately the same, not similar in the way that local dialects resemble one another while remaining distinct. The same arrangement of phrases, the same spectral shapes within each phrase, the same temporal relationships between the parts, as though each male had access to a score that none of them could read, but all of them were reading. A researcher recording one male on a breeding ground in the Caribbean and another researcher recording a different male 100 miles away would bring home, weeks later, the same song. A male humpback, hanging almost motionless 20 feet below the surface, produces this performance not once, but continuously, for hours, for days, repeating the entire song from beginning to end, and immediately beginning again, barely pausing at the seam. The water around him receives the sound in all directions, carrying it outward at roughly a mile per second through the column of the ocean, and the song begins its long transformation the moment it leaves him. The highest components, the frequencies above roughly 1,000 cycles per second, begin losing energy almost at once to the physics of the water, which absorbs high-pitched sound far more efficiently than low. Within a few dozen miles, those upper registers are gone entirely, taken by the sea. What remains and travels on is the lower skeleton of the song, the structural frame that holds the phrases together, stripped of the harmonic richness that was present at the source. The song is being filtered by distance. By the time it has traveled 200 or 300 miles, a hydrophone recording, it would hear something considerably simpler than what the singing male produced. The harmonic detail, the fine texture of each phrase, the upper frequencies that give the sound its tonal color, all of that has been progressively removed, layer by layer, by the absorptive character of seawater at those frequencies. What arrives is bass-heavy, simplified, the structural outline of the original performance, audible but shorn of its detail. Whether another whale, receiving this distant and transformed signal, can still recognize it as the song it began as. Whether enough information survives the filtering to carry meaning across that range is a question that remains genuinely open. No one is sure. There is real evidence pointing in both directions, and no way yet to resolve it cleanly, but the song travels. That part is certain. Consider what the listening ocean contains. On a winter morning in the tropics, the breeding grounds hold dozens or hundreds of males, each one singing continuously, each song identical in structure to every other, the whole acoustic field thick with the same themes repeated at different phases, overlapping and interfering with one another in ways that would be cacophonous to a human listener trying to track any single performance. And yet the songs propagate outward into the deeper water, spreading from the warm, shallow breeding areas into the cooler, denser water below, and some portion of that sound finds its way into the low-velocity layer that runs along the deep ocean, where the refraction of the water holds acoustic energy and carries it far. The low frequencies of the song, those that have already survived the filtering of the upper registers, are the ones best suited to that propagation. They fit the channel the way a long, slow wave fits an open sea. The energy in those low frequencies belongs to a different acoustic world than the world of ordinary experience. A wavelength at 40 cycles per second in seawater stretches roughly 37 meters from crest to crest, not 60 or 70, as at the lower infrasonic frequencies, but still a distance that dwarfs any obstacle the ocean normally presents. A fish, a patch of plankton, an eddy of slightly warmer water, none of these are large enough to meaningfully scatter a wave that long. The sound bends around them as though they are not there, and continues. What can scatter or absorb these frequencies is the sea surface itself, rough and bubble-filled and acoustically lossy, and the depths below, where the pressure is enormous and the physics of propagation change. Between those two boundaries, in the middle layers of the deep ocean, the low-frequency portions of humpback song move with a steadiness that their higher-frequency companions cannot manage. A theme within the song consists of repeated phrases, and each phrase has a shape, a characteristic trajectory in frequency and time that makes it recognizable as belonging to that theme and not another. When Roger Payne and Scott McVeigh described this architecture, they were working from recordings made in the 1960s, carefully listening to playbacks in the dark of a living room, realizing slowly that what they were hearing had the organizational properties of something deliberate and complex. The nested hierarchy, Unit, subphrase, phrase, theme, song was not something they imposed on the data. It was something the data insisted on. The repetition was too precise, the structure too consistent across individuals and recordings to be anything other than a true shared form. And the form changes. This is the part that took several more decades to understand, and it changes things considerably. Every male in a given breeding population sings the same song in a given season, but the song is not the same from season to season. It evolves continuously in the same direction across the whole population simultaneously, with new elements appearing and spreading through the group until the song that will be sung 2 or 3 years from now bears only partial resemblance to the one being sung today. The song updates itself, and every male updates with it, so that the shared version, whatever the current version is, remains shared. The mechanism is imitation. A male hears the song as it is currently being performed and copies it and adds whatever modifications are already spreading through the population at that moment and sings the updated version and is heard by others who do the same. The song is transmitted the way a rumor moves through a crowd, not by any one carrier crossing the whole room, but by the chain of one person hearing and repeating to the next. Except that what is being transmitted is not a simple message but a complex, temporally organized acoustic performance, and the fidelity of the transmission is high enough that the essential structure survives intact even as the details shift. In 2011, a group of researchers published work documenting exactly this process unfolding across the South Pacific over the course of 2 years. A new song type appeared in Australian waters on the eastern coast. Within roughly 2 years, it had spread progressively through 6 separate breeding populations, stretching eastward across the Pacific, each population adopting the new version and abandoning the old one. Not all at once, the spread moved from west to east, one population at a time, as though the song were crossing the ocean on a current that ran from Australia toward the Americas. The song was not physically propagating across that distance as a single pressure wave. The ocean is not quiet enough, nor the signal strong enough, to carry a humpback song from Australian waters to French Polynesia intact. What crossed the ocean was not a sound, it was a memory of a sound. Individual males moved as humpback whales do, following their seasonal routes between feeding grounds and breeding grounds, crossing paths with whales from adjacent populations on those migrations, hearing unfamiliar songs in the water around them, incorporating the new elements into their own performance, and carrying the updated version back to their home population when they returned. The song traveled through minds and throats and bodies, passed from one animal to the next along the biological routes that individual whales already followed, moving through cultural transmission rather than through acoustic propagation. A pressure wave cannot cross the Pacific from Australia to French Polynesia and arrive recognizable, but a whale can make the crossing and carry the song inside it and sing it on the other side. The distinction is precise and it matters. Acoustic propagation and cultural transmission are both forms of communication across distance, but they operate through entirely different physical mechanisms, on entirely different timescales, and with entirely different properties of fidelity and range. A pressure wave travels at roughly a mile per second and loses fidelity with every kilometer. A song carried inside an animal travels at the speed of a migrating whale and can, in principle, cross any distance that whale is capable of traveling, arriving at full fidelity because it has not been filtered by water or eroded by absorption. The two mechanisms overlap. A whale hears a song acoustically and then carries it physically, but the long-range transmission is the biological one, not the acoustic one. This does not make the acoustic propagation irrelevant. The opposite. For the cultural transmission to occur, the song must first be heard. A male must be close enough to another singing male, or to a group of singing males, to receive the acoustic signal with enough fidelity to learn from it. The acoustic range of the song determines how far away a learning male can be and still successfully acquire the new version. And that range is determined by the physics, the frequencies involved, the noise floor of the water, the depth and character of the propagating medium, the season, the geography. The song is always doing both things at once. It is propagating through water as a physical wave, carrying its low-frequency structure as far as the ocean will allow, while simultaneously being incorporated into the repertoire of every male that hears it, clearly enough to copy it, to be carried forward through the population not as a wave, but as knowledge. The acoustic range sets the neighborhood. The cultural transmission takes it from there. There are places in the ocean where these two mechanisms create something almost stratified. Near the center of a breeding ground, the acoustic environment is thick with song, multiple males close enough that the high-frequency detail of the song is intact, the harmonic structure audible, the full version present in the water. Here the learning is easy, the copying faithful, the shared version kept current and uniform. At the margins of the breeding area, further from the dense core of singing males, the acoustic signal has been filtered by distance and the sea. The lower registers remain, carrying the structural frame of the current song, but the finer detail is gone. A male at that distance might hear enough to know that the song has shifted, that the new theme is spreading, that the phrase shapes are different from last season, but not enough to copy the detail precisely. The version he sings might lag slightly behind the current consensus. The fidelity of the cultural chain depends on the fidelity of the acoustic link that feeds it. A humpback calf swimming in the shallows near its mother produces sounds of a completely different character from the songs that adult males sing on the breeding grounds. The calls between a mother and her calf are quiet, barely audible 50 yards away, dropping below the ambient noise of the sea within 200 meters, entirely unlike the broad-frequency performance of a winter singing male. The spatial scale of mother-calf communication is measured in yards and hundreds of feet, rather than in miles. It is a whispered conversation held close, in the warm, shallow water of a calving area, where the acoustic range does not need to reach far, because the relevant other is always near. Between these two extremes, the intimate acoustic bond of a mother and calf, and the basin-reaching performance of a singing male, lies the full range of acoustic social life that humpback whales appear to occupy. Feeding calls exist, used in aggregations, where multiple animals cooperate around a shoal of fish. Contact calls exist, exchanged between animals traveling together, holding a social unit, acoustically coherent, as it moves through open water. Each of these operates at its own spatial scale, and each has a frequency content and a source level adapted to that scale. The quieter and higher pitched the call, the more intimate the context. The louder and lower the call, the further it is meant to carry. Song is the furthest reaching of all these acoustic forms, and it is sung only by males, and only in winter, and only on the breeding grounds, or while traveling toward them. The selectivity of its production is itself a kind of evidence about its function, though what that function is remains genuinely debated. The most straightforward hypothesis is that song serves to attract females and to signal male quality or identity over long acoustic ranges. The evidence for this is suggestive rather than definitive. Females do approach singing males under some conditions, Males sometimes stop singing when a female appears, shifting to other acoustic and behavioral modes of interaction. Whether the song is primarily directed at females or at other males, a signal of competitive fitness, a claim of acoustic territory in the water column, is not settled. Both functions might be operating simultaneously, the song doing double duty in the complex acoustic politics of a winter breeding ground. What is settled is the song's acoustic architecture and the precision of its shared structure. A researcher transcribing a phrase from a recording made on one breeding ground and a phrase from a recording made on another will find, in the same season, the same phrase, the same sequence of frequency contours, the same temporal proportions within the phrase, the same relationship between that phrase and the phrases surrounding it. The song is a community possession held in common by all the males of a population, updated in common, transmitted in common, and produced in isolation, each male singing alone, moving slowly through the water with his sound spreading around him, unaware of most of the other males producing the same performance in the wider ocean. The frequency range of the song makes it legible to human ears in a way that the infrasonic calls of blue and fin whales are not. A person listening to a recording of humpback's song hears something that the brain, shaped by evolutionary history to detect pattern and structure in acoustic sequences, immediately recognizes as organized, not musical in the sense that requires a shared cultural frame. The song does not follow the harmonic rules that Western music uses, or the rhythmic conventions, or the melodic logic that any particular human tradition would apply, but organized, sequenced, having the quality of something deliberate rather than random. The brain reaches for the word music and then holds back because the word carries implications that may not belong there, and because the more honest description is simply structure at multiple nested levels, precisely maintained and precisely shared. It is the nesting that makes it strange. A unit is to a subphrase as a word might be to a phrase. A phrase is to a theme as a line might be to a stanza. A theme is to the full song as a stanza is to a poem. These are not identical relationships. The analogy is imprecise and should not be pushed too far, but the organizational logic is similar enough that the human pattern-recognizing mind finds itself tracking the structure, noticing where a phrase ends and the next begins, registering when the theme shifts, following the repetition, and then the full song ends and immediately begins again, and the tracking continues, and the mind, following the patient unfolding of something that does not need a witness, begins to slow. The songs recorded in the 1960s are not the songs being sung today. The populations that produced those early recordings have been updating their shared performance continuously for decades through cultural transmission, through the chain of hearing and copying and variation and recopying that moves each season's song a little further from the previous seasons. Some of the changes are additions, new units appearing within familiar phrases, new phrases being inserted into established themes. Some are replacements, with old themes falling gradually out of use as new ones spread and crowd them out. The overall direction of change is not random in every dimension. Some properties of the song appear more stable than others, and the rate of change varies across populations and across time, but the general character is of continuous drift, the song always moving, never arriving at a fixed form. This is different from the infrasonic signals produced by other large baleen whales, which appear far more stereotyped within a population, their temporal and spectral structure remaining highly consistent across decades. The 20-cycle calls of a blue whale have changed over recent decades, but in a simpler way, a gradual shift in the center frequency of the whole call type, the same call getting imperceptibly lower year by year as though the entire population were slowly retuning. The humpback song changes differently, not just a shift in one parameter, but a restructuring of the entire hierarchical arrangement, themes coming and going, the nested architecture itself evolving, the community of singers collectively producing something that is recognizably a humpback song at every moment, but is never exactly the same song twice. A winter night on a breeding ground in the tropics, many miles from the nearest land. The water is warm near the surface, cooling steadily with depth. The sky above is clear, the stars very bright, the surface of the sea moving with long, low swells that carry no wind in them, just the memory of a storm somewhere else days ago. Below the surface, the acoustic field is dense with song. 20 males, 30, scattered over the ground, each hanging in the water at a depth of between 10 and 60 feet, each producing the same long performance in isolation, the songs overlapping at every point in the water between them, interfering constructively and destructively, the spectrogram of any given location in the sea, showing a complex layered field of acoustic energy in which the individual songs are threads in a texture rather than single voices. The low-frequency portions of the song travel away from the breeding ground and into the deep ocean. They find the cooler, denser water below the thermocline. They enter the layer where the velocity of sound reaches its minimum and the refraction holds them, bending them back whenever they try to escape upward or downward, carrying them forward through the ocean with the slow persistence of something that has nowhere else to be. Hundreds of miles from the breeding ground, in water 3 miles deep and nearly featureless, a hydrophone on the seafloor records a faint, bass-heavy signal, the structural skeleton of the song, its upper harmonics long since removed by the sea, its lower registers intact and still organized, still carrying the nested pattern of units and phrases in the sequence that every male on the breeding ground is currently producing. The hydrophone does not know it is hearing a song. It records pressure changes at its location, faithfully and without interpretation, and the data it produces must be carried back to a laboratory and examined by a human researcher who will recognize the pattern and trace it back to its origin. The recognition, when it comes, is the product of familiarity. A researcher who has spent years with recordings of this population knows the current song the way a person knows a melody they have heard all season, and can identify the structural signature even in the stripped and simplified form that survives the journey. The song arrived. It traveled hundreds of miles. It lost its harmonic richness. It was filtered by water and compressed by the physics of propagation, and it arrived. The version that arrived was not the version that was sung. It was a degraded copy, missing much of its detail, carrying the frame but not the full texture. Whether this matters to any biological receiver depends on what the receiver needs from the signal, and on that question, the ocean has not yet offered a clear answer. The possibility remains that what matters over long distances is not the detail, but the presence, not the precise spectral character of a given phrase, but the acoustic fact that something is there, organized, repeating, identifiable as the kind of thing it is. A distant whale might not need to learn the song from a faraway signal. It might need only to know that the population exists, that the breeding ground is occupied, that the season has begun. The song is always both near and far at once. Near, it is a complex and detailed acoustic performance, rich with the harmonic structure that gives it its tonal character, legible in full to any male close enough to hear it clearly, available to copy in its current form. Far, it is a simplified signal, a low-frequency trace of itself, stripped by distance of everything but its most durable structure. The same sound at two different ranges is two different things, not because it has changed in itself, but because the ocean has progressively removed from it everything the ocean could take. What remains after that removal is the part the ocean could not take. The lowest frequencies, the longest wavelengths, the parts of the song that sit at the boundary between what a humpback produces and what a blue or fin whale produces. These are the parts that travel on, that find the deep propagation channel, that cover the distances a human mind struggles to hold. A song that began as a performance lasting 30 minutes, produced by an animal the length of a city bus, has by this stage become something more spare. A few low-frequency components, repeating in a sequence, carrying a pattern across 100 miles of open water, arriving at a seafloor instrument as a faint and bass-heavy signal that a trained researcher can still recognize. That recognizability is its own kind of wonder, though wonder is too bright a word for what this hour and this darkness call for. Call it instead a quiet completion. The song left a body, it entered the ocean. The ocean took what it could take, and the song gave it freely, and what the ocean could not take traveled on. In the warm dark of a winter breeding ground, another male is beginning the first phrase of the song's first theme, his voice indistinguishable from the voices of 30 other males doing the same thing in the same water, all of them singing the same song that no one taught them explicitly, that they learned by listening, that they will update by the end of the season, that will be different next year, and the year after, and the year after that, drifting slowly through the generations like something that has no destination, no final form, no last note. A phrase ends, the next begins. The song continues across the dark water, patient and low, carrying its structure forward as far as the ocean will allow, and further than that through the bodies of the animals that carry it. And the night holds all of it, the near version and the far version, the full performance and the stripped trace, the sound in the water and the memory of the sound in the minds of the whales that will carry it westward when the season turns. Far from the breeding ground, in the long quiet between the surface and the floor, the signal moves. It does not hurry. The water ahead of it is the same water the water behind it was a moment ago, cold, dark, vast, indifferent to what it carries. The song has no knowledge of how far it has come or how far it is yet to travel. It is simply a pattern in the pressure of the ocean, repeating, fading at the margins, carrying the structure of something that was once a performance and is now a trace. The water that holds it has held other traces, older songs, earlier seasons, all the long acoustic history of this population, singing into the same ocean over the same centuries, and none of those traces remain. Only the current one remains, moving outward from this season's breeding ground in this winter toward a silence it will eventually reach. The silence will come. The signal will fall below the noise floor of the deep sea, buried under the murmur of currents and the low frequencies that fill the ocean from sources too distant and too numerous to identify. At some distance from the source, the song will become indistinguishable from the background, and it will cease in any meaningful sense to exist as a signal. The ocean will have taken the last of it. What was once a detailed acoustic performance, then a simplified structural trace, then a barely detectable low-frequency repetition, will have merged back into the ambient acoustic texture of the sea. But at this moment, this particular moment, in this particular winter, in this particular stretch of warm ocean, the signal is still there, moving slowly, losing a little more energy with each passing mile, but still organized, still carrying its pattern, still the song, in the attenuated and simplified form that distance has made of it. The males on the breeding ground will sing until the season ends, and then they will fall silent, and the breeding ground will become ordinary ocean again, neither quieter nor louder than any other patch of open sea. The whales will leave, spreading north and south toward feeding grounds, carrying with them the current version of the song, updated, as it will be, from whatever variations emerged and spread over the course of the season. They will not sing again until winter, and when winter comes, they will begin again, wherever the breeding ground is for their population, and the song they sing will be the song they carry, the one they learned by listening, the one they will update again by listening, the one the ocean will again receive and carry forward as far as it can. The song does not accumulate. Each season's version replaces the last in the population's shared performance, the old one passing out of use as the new one spreads. The chain of transmission, not a record but a present, always the current version and not the previous ones. The ocean holds no archive of past seasons. The water that carried last winter's song has moved on, mixed and dispersed. The pressure patterns it briefly contained, long since absorbed by other pressure patterns and lost. What persists is only the living version, in the living animals, ready to be sung again when the season returns and the males gather in the warm water and begin, somewhere in the dark water, at a depth of perhaps 30 feet, a male is midway through a theme. The phrase he is in will end in a few seconds. The next phrase will begin almost immediately, following the arrangement that every other male in this ocean, in this season, is also following. The water around him carries his voice outward. It carries the voices of the others outward. It takes the high frequencies first, then the middle, then, slowly, and at far greater distances, the low. What reaches the deep ocean and travels on is the lowest and most durable part of all of it, a quiet, bass-heavy signal moving through cold water in the dark, carrying the structural outline of a song that exists, in full, only in the bodies of the animals producing it, and nowhere else in the world, and for no longer than the season lasts. On the floor of the North Atlantic, in water so cold and dark that no season has ever reached it, a machine listened. It was built in the early years of the Cold War, anchored to the seafloor along ridges and continental margins, cabled back to shore stations where technicians sat in rooms with humming equipment and classified charts. Its purpose was to hear submarines. Its hydrophones pointed outward into the dark water, sensitive to the low frequencies that carry furthest in the deep ocean, recording without pause through winter and summer and the slow turn of years. It heard what it was built to hear, and it heard a great deal more. The network stretched across the North Atlantic and into the Pacific. Dozens of listening stations, hundreds of hydrophones, each one taking in the full low-frequency acoustic life of the ocean, compressing it into data streams that moved up the cables and into buildings on shore. For decades, the recordings accumulated. The technicians noted the submarines. Everything else was set aside. Then, in the early 1990s, some of those recordings reached a scientist named Christopher Clark, working at Cornell University. The Navy had begun declassifying portions of the archive, and Clark was given access to years of hydrophone data from the North Atlantic. He was a bioacoustician. He had spent his career listening to the sounds that whales produce, and when he sat down with the old Navy recordings and began to move through them, he found something he had hoped for, but had not been certain he would see. The calls were there, across the full record, threaded through years of accumulated data, were the slow infrasonic signals of large baleen whales, the deep repetitive pulses that move through the ocean at frequencies near 20 cycles per second, below the range of any unaided human ear. They were not faint or rare, they were everywhere, and what the network's geometry allowed, which no single hydrophone could, was the triangulation of their sources. A call recorded simultaneously at stations separated by hundreds of miles carried in its timing a precise location. The hydrophone closer to the source heard the signal a fraction of a second before the one farther away. From those differences, small, exact, calculable, a position could be fixed. Not a rough region, a point, a single animal, or a group of animals somewhere on the open ocean producing sound that had crossed hundreds of miles of deep water and arrived intact at 3 or 4 different listening posts at once. Clark and his colleague William Ellison published what they had found, and the picture it gave of whale acoustic range was something that overturned the prior estimates completely. Individual blue whale calls were being detected simultaneously by hydrophones thousands of kilometers apart. Not a similar call from 2 different animals in different places. The same call, the same pulse, the same moment in time, arriving across an ocean at stations that had never been intended to hear anything alive. The ocean had been full of these signals all along. For decades, they had been recorded faithfully, filed away in a classified archive, and no one working with whale acoustics had known. The SOFAR channel had been carrying them the entire time, the way it carries any low-frequency sound that enters it near its axis, bending the energy back toward itself, holding it between the thermocline above and the increasing pressure below, guiding it along paths that touch neither the wave-churned surface nor the absorptive sediment of the floor. A blue whale calling near the channel axis, at depth, was coupling its voice directly into the most efficient acoustic waveguide on the planet. The signal traveled outward at roughly 1,500 meters per second. In a single hour, it had moved more than 3,000 miles of water. In a day, it had crossed an ocean. The question the data could not answer, and that remains open still, is what the animals themselves were achieving across those distances. There are several serious ideas. One is that blue and fin whales in a given ocean basin are acoustically aware of one another at all times, that the infrasonic calling of scattered individuals creates a kind of acoustic census of the population, giving each animal some rough sense of where others are located, how many are calling, whether the distribution has shifted. On this picture, the ocean is not empty space through which isolated animals move in silence, but an acoustic medium that each animal samples continuously, the way a fish might sample current or temperature. The calls are not directed messages. They are more like a presence, a continuous broadcast of location and identity, received by all within range and interpreted over the course of hours or days rather than seconds. Another idea, not incompatible with the first, is that the calls function in mate attraction and spacing among males during the breeding season, when calling rates climb and the acoustic competition becomes measurable even in raw hydrophone data. On this reading, the extraordinary range is not necessary for most of the signal's function. A male calling at full source level needs only enough range to be heard by the nearest receptive female, and that range, even in a noisier modern ocean, is still very large. The basin scale propagation is, on this view, a byproduct of a system tuned for long range, not a system tuned for continent-to-continent communication specifically. A third possibility, harder to test, is that the calls carry information about feeding conditions. Blue whales aggregate at patches of krill that are themselves structured by ocean temperature, current, and upwelling, conditions that shift across seasons and years. An animal that has found a dense patch and is vocalizing intensively near that location is broadcasting its position to all others within acoustic range. Whether that broadcast is intentional in any sense that word applies to an animal, no one can say with confidence. What can be said is that the distribution of calling whales, tracked through the Navy hydrophone network, has been shown to shift across ocean basins in patterns that correspond to known shifts in prey distribution. The animals that can hear one another are, on average, better positioned to find the food. None of these ideas fully closes. The best current understanding is that all of them may be partially true, and that the calls are doing several things at once, the way most biological signals do. What the hydrophone data established, firmly and beyond revision, is the range within which any of these functions could operate, and that range, before any noise was added to the ocean, was an entire ocean basin. To understand what the ocean sounded like before it was full of ships, it helps to think about noise the way an engineer would, though without the engineer's clinical detachment from what it means. Every acoustic signal has a source level, the amplitude of the sound at the point of origin. Every environment has a noise floor, the level of background sound already present, against which the signal must rise to be detectable. The gap between the two, measured in decibels, is the signal-to-noise ratio, and it is not the absolute level of the signal that determines how far it can travel. It is how far the signal can travel before its amplitude, diminished by spreading and absorption, falls below the noise floor of the environment it is traveling through. A blue whale call leaves its source at roughly 188 decibels, measured by the underwater standard. It spreads outward through three-dimensional space, and its intensity falls with distance. In the SOFAR channel, where the waveguide geometry confines the spreading to something closer to cylindrical than spherical over long distances, the loss is slower than it would be in open water. Even so, after 1,000 miles, the signal has fallen substantially from its source level. The question is whether it has fallen below the noise floor of the ocean. In a quiet ocean, and the ocean was quieter before the middle of the 20th century, because the machinery that crosses it now was not yet there. The noise floor at frequencies near 20 Hz was set by natural sources. Seismic microseisms, generated when ocean swell interacts with the seafloor, contributed a broad background hum across low frequencies. Distant storms added their own acoustic signature. Ice in polar regions contributed cracking and grinding sounds. And the biological noise of the ocean itself, the collective sound of millions of marine organisms, was part of the ambient level. All of these sources were real, and none of them was trivial. The pre-industrial ocean was not silent, but it was in the low-frequency band that blue and fin whales use, measurably quieter than the ocean has been for the past 60 years. The difference was shipping. A cargo vessel moving across the ocean at ordinary cruise speed is a substantial source of low-frequency sound. The dominant contribution comes from the propeller, a massive rotating structure that develops regions of low pressure on its blade faces, and where that pressure drops low enough, generates cavitation, the rapid formation and collapse of vapor bubbles that produces broadband noise across a wide frequency range, with most of its energy concentrated below a few hundred hertz. A single large vessel might radiate sound at source levels of 180 decibels or more at frequencies where blue whale calls propagate most efficiently. The SOFAR channel receives that sound and carries it, just as it carries the whales outward in all directions from the ship's position. In the 1960s, a researcher named Gordon Wins compiled measurements of ambient ocean noise across a wide range of conditions and frequencies. The resulting curves, which came to be called the Wins curves after him, documented what the ocean actually sounded like at different noise levels: quiet sea state, moderate sea state, heavy traffic, and across the range from a fraction of a hertz to 100 kilohertz. At low frequencies, in the range occupied by blue and fin whale calls, the Wenz curves showed that the ambient noise level in heavily traveled ocean regions had already risen substantially above pre-industrial baselines, and that the primary contributor in those regions was distant shipping traffic. The ocean, at low frequencies, in most of the regions where large baleen whales live, is now substantially louder than it was when those whale calls evolved, not louder by a small increment. Louder by something on the order of 10 to 15 decibels in many ocean regions, with some areas more affected than others, depending on proximity to major shipping lanes. 10 to 15 decibels is not a minor difference. In acoustic terms, it represents a large change in the effective signal-to-noise ratio experienced by any animal trying to detect a conspecific call against the background. The practical consequence of that change can be stated simply. Before commercial shipping reached its modern scale, a blue whale call propagating through a quiet North Atlantic could travel, on modeling estimates, something like 1,600 kilometers before its amplitude fell below the background noise level. The animal at the receiving end, another blue whale, 1,000 miles away, would detect the call. After that same call propagates through the modern ocean, with its noise floor elevated by distant ship traffic, the call becomes undetectable at a much shorter range. Modeling work by Clark, Ellison, and others estimated that in some heavily trafficked ocean regions, the effective communication range of large baleen whales has been reduced by as much as 90% compared to what it was before the shipping lanes were established. And 90% is not a catastrophe, in the sense that the animals have not stopped calling, have not stopped moving, have not vanished from the hydrophone records. They are still there. But the acoustic space available to them, the volume of ocean within which a calling animal can be detected by another, has shrunk to a fraction of what it was. An ocean that once made a whale's voice available across an entire basin now makes it available across a much smaller region. Whatever functions that range was serving, the loose acoustic census, the mate finding, the food location signal, all of them operate now within a space that is, acoustically speaking, much more confined than the space the calls evolved to work in. There is a subtler change that the hydrophone records document over decades of continuous listening, and it concerns not the range of the calls, but the calls themselves. Researchers working with recordings of Northeast Pacific blue whales, collected systematically from the 1960s onward, noted something in the long-term record that took some time to interpret. The calls were changing in frequency, not in structure. The temporal pattern, the duration, the general shape of the signal on a spectrogram were all consistent with blue whale calls, and recognizably the same across the full record. But the center frequency of the calls, the pitch, was drifting upward. Slowly, year by year, across decades, Mark MacDonald, John Hildebrand, and Sarah Webb, analyzing the long-term record for the Northeast Pacific population, documented the trend in detail. Between the 1960s and the early 2000s, the center frequency of blue whale calls in that population increased by approximately 31%. 31% upward shift in frequency, sustained across 4 decades. It is measurable, it is documented, and it raises a question that no one has yet fully answered. The simplest and most alarming interpretation that blue whales were actively adjusting their call frequency upward to stay above the rising low-frequency noise floor generated by shipping does not fit the data well. The noise floor that shipping creates is largest precisely in the low-frequency range, around and below 20 Hz. If the animals were shifting upward to avoid that noise, the expectation would be that the shift was correlated in time and magnitude with the rise in shipping noise. The correlations are not tight. The noise has risen sharply over the same period, but the frequency drift in the calls does not match its trajectory closely enough to make a simple avoidance story convincing. A different hypothesis, and one that some researchers find more plausible, is that the frequency shift reflects changes in the population itself, specifically changes in the body size of calling males. Blue whale calls are produced, at least in part, through the physical resonance properties of the vocal anatomy, and larger animals produce lower frequency calls. Blue whale populations were heavily hunted through most of the 20th century, with hunting most intense on the largest individuals. After the cessation of commercial whaling, the populations that survived were, on average, smaller bodied than pre-whaling populations. As those populations recovered and individuals grew across generations, the average body size, and with it the average call frequency, may have been drifting in ways that shifted the population level average upward. Or it may have been drifting downward as animals grew toward pre-exploitation sizes, and the observed frequency increase might reflect something else entirely. The honest answer is that no one is yet certain. The frequency shift is real. The mechanism behind it is not settled. There are good ideas and real evidence for and against each, and the observation itself stands intact, regardless of what eventually explains it. What it adds to the picture is a reminder that the acoustic identity of a whale population, the specific spectral signature that carries information about who and where a call comes from, is not fixed and permanent. It changes on timescales that are long by human standards, but short by biological ones, and it changes in ways that the instruments built to listen across ocean basins are sensitive enough to detect. The instruments themselves are still there. The network that was built to find submarines and then repurposed to find whales has continued in various forms. Parts of it have been decommissioned and parts rebuilt. New hydrophone arrays, operated by research institutions and international monitoring organizations, supplement the older infrastructure. The continuous low-frequency record of the North Atlantic and parts of the Pacific is now measured in decades, and in that record, quiet and technical and mostly unpublicized, are the acoustic lives of the largest animals that have ever lived on this planet. Not as occasional recordings made by research vessels, but as continuous presence, season after season, year after year. The record shows the seasonal patterns clearly. Blue whale calling intensity in the North Atlantic rises through autumn and into winter, then subsides during summer. Fin whale doublets cluster in the same months, the clockwork pairs of pulses building in density through the cold season and thinning again as summer approaches. The calls are not uniformly distributed across the basin. They cluster in certain regions in certain months, areas of elevated prey density, areas of known aggregation, areas near historical feeding grounds, and they shift, year by year, in ways that correspond to shifts in ocean temperature and the distribution of the cold, nutrient-rich water that concentrates the krill and small fish on which the great whales feed. The ocean is not static. Its temperature shifts across seasons and across years and across the longer cycles of climate variation. The krill patches move with the temperature. The whales move with the krill, or at least appear to, though the relationship is not simply mechanical. An animal the size of a blue whale does not turn on a dime in response to every patch of cold water. and the timing of its movements involves factors that overlap in complex ways with the acoustic signals the hydrophones record. What the network makes possible is a view of the whole, a slow, wide perspective that no individual research vessel could achieve, a picture of an entire population distributed across an ocean basin, calling and moving and calling again over the full arc of a year. That perspective changes what it is possible to know about these animals. Before the hydrophone networks, the acoustic range of large baleen whales was estimated from the physical properties of their calls, combined with what was known about low-frequency propagation in the ocean. The estimates were large, hundreds of miles, but they were theoretical. The network made them empirical. A researcher sitting at a shore station in the 1990s, reviewing data that had been collected years before in a military archive, could trace the position of a calling blue whale across days and weeks, not from tagging data, not from visual observations, from sound alone. The animal was never seen. It was known only as a pressure wave in the water, a signal on a spectrogram, a set of arrival time differences between hydrophones that reduced to a point on a chart. There is something in that knowledge, arrived at in that way, that carries its own particular weight. The animal existed in the data record as pure acoustics. Its body, enormous, warm, breathing, moved through the dark ocean far from any ship or person, calling in frequencies no human ear can hear, and what reached the instruments was a mathematical abstraction of that calling, stripped of everything except frequency and timing and amplitude. And yet from that abstraction, a life in the ocean could be partly reconstructed. Not fully. The network's picture has its gaps, regions of the ocean where no hydrophones were placed, times of year when calling rates dropped and the animals fell partly silent. The internal experience of the animal, if that phrase means anything at all, was not available then and is not available now. What the calls are saying to one another, in whatever sense a 20 Hz pulse can be said to say anything, remains only partly understood. The science can characterize the signal with precision. It can estimate the range. It can describe the seasonal and geographic patterns of calling. It cannot yet translate, but translation may not be the right frame for what these signals do. Human language is structured for translation, built from discrete units with stable meaning, assembled by a grammar whose rules allow a thought to move from one mind to another in the form of air pressure waves. The infrasonic signals of blue and fin whales may not work that way at all. They may carry information the way a chemical gradient carries information, not as a message with content, but as a pattern that modifies behavior, changes the probability of movement in one direction or another, signals presence or absence or intensity, without specifying any particular thing. The information is real, the channel is real, the range is extraordinary. Whether there is anything in it that resembles meaning, in the sense a human would recognize, is a question the data does not answer and may never answer cleanly. What the data does answer is the physical fact of connection. Two animals, each the length of an aircraft, and heavier than anything else alive, separated by 1,000 miles of cold, dark water, are nonetheless acoustically connected, each within the other's detection range, each capable of receiving the infrasonic signals the other produces, each sitting inside an ocean that acts as an amplifier and a waveguide and a medium of extraordinary efficiency at the very frequencies those animals use. That connection is not metaphorical, it is physical, it can be measured. It was measured across decades of inadvertent listening before anyone knew they were measuring it. The shipping lanes run through that acoustic space. The major transoceanic routes cross the North Atlantic on paths that have been laid down over a century of commercial navigation. The North Pacific lanes connect the ports of Asia and North America through waters that blue and fin whales have been using as acoustic channels for far longer than ships have crossed them. The vessels that move those routes, tens of thousands of them in any given year, each contribute their low-frequency propeller noise to the ambient field. The contributions from individual ships add together in a way that is not simply arithmetic. Acoustic energy from multiple sources combines in complex patterns, sometimes reinforcing and sometimes partially canceling, but the overall effect on the low-frequency noise floor is cumulative and sustained, and measurable at any hydrophone in the basin. There have been moments, largely accidental, when the shipping noise has briefly fallen, and what those moments revealed was instructive. In the days following the 11th of September, 2001, commercial air traffic over North America halted almost entirely for several days, and maritime traffic in some regions also declined. Researchers who had been maintaining hydrophone recordings in the Bay of Fundy, an area used by right whales, which call at similar low frequencies, documented a measurable reduction in ambient low-frequency noise during that period. The background noise level dropped, and the measurements of stress hormones in right whale fecal samples collected during those same days showed lower levels than in samples collected before or after. The animals were, in some biological sense, less stressed when the ocean was quieter. It was a natural experiment that no one planned, measured in the data by its absence rather than its presence. The North Atlantic and North Pacific have no equivalent of that accidental quiet. The shipping lanes run continuously, but there are efforts, growing in number and changing in their ambition, to reduce the noise contribution of individual vessels. The dominant source of propeller cavitation noise is not an unavoidable property of the physics. It is partly a consequence of propeller design and vessel speed. A propeller designed to minimize the low-pressure regions where cavitation initiates can reduce the noise output of a vessel substantially. Slow steaming, which simply reduces the ship's speed from typical cruising speeds to lower values, reduces cavitation noise substantially, in some cases by 40% or more in total acoustic energy. The International Maritime Organization, which coordinates standards for commercial shipping across member nations, adopted voluntary guidelines in 2014 directing shipbuilders and operators toward quieter propeller designs and operational practices. They are voluntary. Compliance varies. The total effect on the basin-wide noise floor is difficult to measure in a system as large and complex as an ocean, but the direction of travel in the engineering is understood. The tools exist. The reduction is achievable. There are also proposals in various stages of development to reroute certain seasonal shipping lanes away from known whale feeding and aggregation areas, or to implement seasonal speed reductions in specific regions where whale calling intensity is highest. The logic is straightforward. A ship that passes through a region where whales are aggregated and calling at reduced speed contributes less noise for a shorter time relative to the distance traveled, and leaves behind it a smaller acoustic footprint per mile than a ship moving at full speed. The whales in that region during that season experience a noise floor that is measurably lower. Their effective communication range extends somewhat farther outward. The acoustic space they can use is slightly larger than it would otherwise be. These are not dramatic solutions. They are incremental and partial and operate within a commercial system that has its own momentum and constraints. The ocean will not become quiet. The ships will continue to cross it. But the difference between a noise floor that is 15 decibels above the natural background and one that is 8 or 10 decibels above it is in the geometry of acoustic detection, not a small difference. Measured as communication range, it corresponds to a substantial volume of ocean, millions of cubic miles of water, through which a whale call can propagate and be heard or cannot. What those extra miles mean to an animal calling in the dark, below the reach of any light, at a frequency no person will ever hear unaided, is not known with precision. The animal does not know that its effective range has been reduced or partially restored. It calls, because something in the physiology and the season and the acoustic context drives the calling, because the signals go out into the water and other animals respond or do not respond in ways that shape behavior over days and weeks. The mechanism is biological and ancient and does not require that the animal understand the physics of its own voice, but the water remembers it anyway. A call that leaves a blue whale in the North Atlantic in midwinter propagates outward through the SOFAR channel, following the long sinusoidal paths that the thermocline and the pressure gradient between them maintain. The signal loses a fraction of its energy to the water itself, a fraction so small at 20 hertz that after 1,000 miles it is still negligible. It loses more to geometric spreading, the inevitable dilution of a finite amount of acoustic energy expanding outward through a large space. It loses more still in the modern ocean to the noise floor that shipping has raised, and at some distance shorter than it once was, longer than it might have been if the propellers were quieter, it drops below detectability and becomes part of the background. The background itself is not empty. It is layered with signals from other animals, other ships, the slow seismic murmur of the planet's crust, adjusting itself at spreading ridges and subduction zones. The ocean at low frequencies is acoustically dense, not acoustically bare, a full and complex acoustic medium that has been in continuous motion for as long as there has been water on this planet. The signals that whales add to it are old. The signals that ships add to it are new. Both are real, and both are part of what the hydrophones record when they listen to the deep frequency life of the sea. At the core of all of it, the physics, the channel, the calls, the instruments, the noise, the gradual efforts at reduction, is a fact that is simple and does not become less true the longer it is contemplated. The largest animals alive are acoustic animals in a way that has no real parallel among the creatures of the land. They live in a medium that does not scatter or absorb their voices the way air absorbs and scatters sound. They produce calls at frequencies precisely suited to that medium's most efficient waveguide. They do this across seasons and years and in patterns that suggest the signals matter, that something is being accomplished at range, even if the nature of that accomplishment is not yet fully legible. And they have been doing it in one form or another for long enough that the anatomy required for it has been refined across millions of years of selection, while the ocean itself has remained largely stable in its deep acoustic structure. The thermocline has been deflecting sound downward since before the first whale entered the water. The pressure gradient of the deep ocean has been bending sound back toward the axis since before there were ears in the sea to hear it. The channel was there, waiting, ancient and patient in the way that physical structures are patient, holding nothing and excluding nothing, simply the result of the way water behaves under temperature and pressure gradients at a certain range of depths. When the first animals with the physiology to produce and detect very low frequency sound came to occupy the deep ocean, they entered a medium already structured to carry their voices across distances that no land animal would ever need to consider. The voices are still crossing it. Somewhere in the North Atlantic, in water that is dark and cold and very far from any shore, a blue whale calls. The sound it makes is below human hearing. It lasts perhaps 20 seconds. It travels outward in all directions at 1500 meters per second, expanding in a sphere that slowly flattens as the channel geometry acts on it, bending the energy back toward the axis, holding it in the waveguide, guiding it away from the absorptive seafloor and the scattering surface. In an hour, the signal has moved across a distance wider than the length of a large nation. In a day, it has crossed a sea. Another animal, somewhere far away in the same basin, receives it, not as a sound in the human sense, as a pressure wave against its body, picked up by the same biological structure that produces its own calls, processed in the neural architecture that has been shaped over deep time to make something of these particular patterns. Whether that processing constitutes perception in any sense, close to what a human means by that word, is not known. The animal is very old in the evolutionary sense and very different, and its inner life, if it has one, is opaque to the instruments that track it. What is not opaque is the signal itself. The signal is real. Its path through the ocean is real, measurable, reproducible. The SOFAR channel that carries it is real, a feature of the ocean's thermal and pressure structure that can be mapped and modeled and confirmed by instruments. The source level that sends it outward is real, documented across dozens of recordings. The arrival at the distant hydrophone is real, logged in archives that have been accumulating for decades. All of this is real and known, and the knowing has not reduced its weight. The ocean moves at the surface in waves driven by wind, visible and familiar to anyone who has stood at its edge. Below the waves, in the thermocline where temperature falls steeply and light fades, the water is quieter and colder. Below the thermocline, in the permanent dark where no light has ever reached and no storm has ever stirred the water, the ocean is quiet in a way that has nothing to do with silence.